So once again, a little more of the same. It's just each quadratic is unique in what its properties reveal. And in this case, we're asked to graph f of x equals x squared minus 2x plus 3 by using its properties. So we'll start off by using, or by finding rather, the axis of symmetry. Now the reason why we start off with the axis of symmetry and vertex, if you haven't noticed as of yet, is because depending on the nature of the parabola, the nature of the quadratic, whether it's opening up or down, and the position of the vertex, we might be able to tell it doesn't have any x-intercepts just based on the properties of the axis of symmetry and the vertex and the leading coefficient. So in this case, first off, I guess we should say the leading coefficient is 1. That means it does open up. So our axis of symmetry, x equals negative b over 2a. And again, and that's the form ax squared plus bx plus c. So in this case, that is negative, b is negative 2 over 2 times a is 1. So that does equal negative 2 is just 2. So our axis of symmetry is x equals 1. Which leads us to our vertex. We know that the x value is going to be 1, and f of 1 equals 1 squared minus 2 times 1 plus 3. So that's 1 minus 2 is negative 1 plus 3 equals 2. So our vertex is at 1, 2. So what does that tell us? Just what I was revealing, what I said it might reveal earlier. Our vertex is at 1, 2. So we'll go ahead and put 1, 2. There's our vertex. And it opens up. So that tells us what in regarding the x-intercepts. We don't have to look at the quadratic, or we don't have to look at the quadratic formula. We don't have to look at the discriminant. We just know that because the vertex is at 1, 2 and it opens up, there are no x-intercepts. It's already, the vertex is already above the x-axis, and we're only going to go up. So now we'll look at the y-intercept. That would be f of 0 when x equals 0. So f of 0 equals 0 squared minus 2 times 0 plus 3, which equals 3, which means our y-intercept is at 0, 3. So 0, 1, 2, 3. Now by symmetry, that means we have a point at 1 on the other side, which would be 2, and the same y value, the other side of the axis of symmetry, if we wanted to put that invisible line right here. Since there's a point at 0, 3, we know there's a point at 1, 3 as well. Or excuse me, at 2, 3 as well on the opposite side of the axis of symmetry. Let's go ahead and find a couple other points. How about x equals 3? At x equals 3, we have f of 3 equals 3 squared minus 2 times 3 plus 3, which equals 9 minus 6 is 3 plus 3 equals 6. So that gives us the point 3, 6. We'll go ahead and plot that point as well. 1, 2, 3, 1, 2, 3, 4, 5, 6. Now we could find algebraically f of negative 1, or we could simply say, well, 3, 6, that's 2 to the right of the axis of symmetry. So we're going to have a point 2 to the left of the axis of symmetry, or at x equals negative 1, we're also going to have a value of 6. And again, we could put that in as far as an actual algebraic solution is concerned, or we could just simply use symmetry. Either way, we'll get the point 1, 6. If we plug in 1, 1 squared minus 2 times 1, that's 1 minus, negative 1 squared is 1 minus 2 times negative 1, that'd be plus 2. So 1 plus 2 is 3, plus 3 is going to be 6. that gives us this parabola. We'll connect the dots for our upward opening parabola, put arrows at the end to indicate in behavior that it is defined infinitely in both directions. It's just going to keep going up and out.